I'm Lauren Madison from the Center for Energy Efficiency and Renewable Energy at UMass Amherst. It's great to see so many people here today. I sent a link out to the slides earlier. If you didn't get that, I'll put it in the chat so you can have a copy of those. And we are recording this, and we'll send out a link to the recording as well as information on CEUs within the next week or so. Throughout the session, you can put any questions in the Q&A. Please use that instead of the chat. And we might answer some as the session goes on if there is something easy to answer in writing, but we will also have time for questions at the end. And with that, I will introduce our speakers. Thanks to Mike Reagan from Mitsubishi Electric and Alex Claremont from DXS New England for joining us today. And I will pass it over to Mike to introduce yourself and get started.
Thank you very much, Lauren. And thank you everybody for attending today's presentation on heat pumps and VRF technology. We'll be going through an overview of heat pump technology as well as getting into several application-specific examples and how we are going to be arming ourselves to approach a building with the necessary info we need to know about how to approach a design from the first site visit. So we're excited to have the opportunity to go over this information. Looks like we have a very good crowd today. My name is Mike Reagan. I'm a commercial area sales manager for Mitsubishi. I have over 6 years experience working with heat pumps and VRF technology and 10 years of experience designing refrigeration and HVAC systems. I'm joined today by Alex Claremont of DXS New England. Alex, if you'd like to introduce yourself.
Thank you, Mike. Thank you, Lauren, for the kind of introductions. Thank you, everybody, for joining us today. My name's Alex. I am originally from north of the wall up in Canada. I am a McGill University Mechanical Engineering graduate. And I've been with DXS New England for 3.5 years. So we'll get started today. So let's talk about heat pumps. It's what I do all day, every day. And I went into this industry 3.5 years ago and went right to the part of it that deals with everything heat pumps. Now we could talk about heat pumps for about 17 hours, but Lauren said we only have a couple hours here to talk about heat pumps. So we'll try to make it nice and short. So this is our agenda for today. We'll first start by going over an introduction of different types of air source heat pumps. Then we'll talk about the different types, refrigerants, efficiencies, cold weather operation, maintenance, then some applications and some ventilations and some resources as well, helpful for you guys. So let's start from the top and talk about how heat pumps work. So a heat pump is no different from the refrigeration cycle, such as your fridge or your car air conditioning. So something important to remember with heat pumps is that they move heat from one environment to another through a temperature gradient. Now, if we go back to the fridge example, it actually rejects heat from inside your fridge to your kitchen, and it actually makes your kitchen warmer. This process of moving heat is done through the refrigeration cycle. Now, it's actually 4 components. You might have seen this before, but it's 4 basic components to any refrigeration system. And it's a compressor, a condenser, an expansion device, whether that's a thermal expansion device or an electronic expansion device, and an evaporator. In some heat pumps, the expansion device lives in the condensing unit, such as a mini split, while in other devices, such as VRF, which we'll get into, the expansion device actually lives in the indoor unit. Now, what's a heat pump? Again, it's the same as your refrigeration cycle, but you can reverse the flow. Your outdoor coil turns into your evaporator, and your indoor coil actually turns into your condenser. You often hear Mike and I refer to the machine outside as the outdoor unit, as it's not always the condenser. It's only really the condenser when the system's in cooling mode. In the winter, it becomes the evaporator. Now, how do you actually reverse this cycle? You don't just turn flow the other way. The flow always goes through the compressor in the same direction. You actually have this device here called the reversing valve. And in the summer, you send discharge gas off the compressor to the condenser outdoors. This real hot gas can actually get cooled by warm-ish air outdoors. In the wintertime, you actually send the discharge gas right to the indoor units, which actually becomes the condenser coil. Now, again, here with your house, the same system in the summer is taking heat from inside and rejecting it outside. And in the wintertime, you take heat from outside and you actually bring it inside the house. Now you're gonna ask me, Alex, does air at 0 degrees have any heat outdoors? Is that air useful? Well, it actually does. And unless you had absolute zero, for refrigerant, it's really just another line on the pH diagram that it can use, that, that air at 0 degrees. So we'll talk about temperatures and efficiencies a little bit later and how this affects heat pumps. But for a lot of heat pumps we're seeing today, there's no issues with heating at our temperatures here in this climate. Now, why use heat pumps? What's the benefit? So heat pumps are actually used in cooling everywhere. We'll talk about efficiencies of the different types of heat pumps for cooling, but electrifying heating is really where heat pumps come into play. With electric heat, 1 kilowatt of heat from the grid gets you 1 kilowatt of heat. With heat pumps, you can move about 2 to 5 from the grid. So you actually get more heat from the heat pumps and you're actually drawing from the grid. So now if you're using electricity, you can actually use clean electricity, whether that's from the grid or from on-site generation. So now this slide kind of talks a little bit about the progression of a very specific kind of heat pump technology over the past 15 plus years. So first we want to start by defining inverterization, which is kind of the title of this diagram that we're looking at. So we're going to talk about this a little bit later, but essentially inverterization means conversion to heat pump and variable speed compressors. And that applies to both residential single splits, but it also applies to, in the commercial market, it actually applies to usually to VRF. And this is showing the adoption of this very specific kind of technology. Again, here, this is just commercial, but it basically went from nothing about 15 years ago or so plus, and to about 10% 6 years ago. And it's growing quite rapidly, and it's projected that it's going to double again in the next 5 years. By the way, here on the slide, we see 40% of the current global market adoption of this type of technology. We think this is probably in an aggregate of the rest of the world. If we look at countries that are actually further ahead on electrification, we think this number is actually probably higher. We think the US can probably get higher than that. So this is going to be a little bit of our basic overview of our structure for today, comparing the different types of heat pumps. Now, if we look at air source and water source heat pumps, those are two kinds of heat pumps we're really going to be talking about today. They both use electricity, and they're both used for space heating and cooling. Both the air source and water source are starting to be used for domestic hot water, and we'll get into that in a little bit. The biggest difference is that for air source, they use air as the heat sink or heat source to reject or absorb heat. For water source, as the name implies, they use water. So whether that's water from a gas-fired boiler loop or whether that's from geothermal. And when it's from geothermal, it's actually called ground source. In terms of efficiencies, we'll get into that in a little bit. On the air source side, they can be up to 5 times as conventional heating, as we previously mentioned, as they actually transfer heat. And on the water source side, they do tend to have slightly higher efficiencies in air source heat pumps, but they do require some additional pumps and some additional equipment on the water side. In terms of site implications for air source heat pumps, they do require either space on the ground or on the roof. And for water source, they'll use a water, so they'll usually use they'll need a loop. In terms of cost, we're going to dive into a little bit different options and the different kinds of air source heat pumps. So we'll talk about that in a little bit. But again, this is kind of a big slide, but it's just to let you know that if someone tells you, hey, I have an air source or a water source heat pump, that's only really part of the story, because all this really explains is the heat source or heat sink. And this is a perfect segue into this next slide, which actually breaks down air source and water source heat pump even more. So in an air source heat pump, you actually, usually if you just hear the term air source heat pump, that's usually referred to as an air-to-air machine, which is where an outdoor machine is extracting and rejecting heat to the outside air and then delivers heating and cooling to the space with refrigerant lines tied to ductless or ducted central unit. Now, this can also be air to water, and we're going to talk about air to water heat pump chillers in a little bit, where the outdoor unit actually rejects and absorbs heat from the outside air, but delivers heating or cooling to the space using water. These types of systems could also help for domestic hot water as well. Now, water source heat pump is usually known as water to air, which is where you have a condenser water loop in a building and you have a bunch of water source heat pumps that heat or cool the space. But there's also water to water systems, which we'll talk about in a little bit. And those are also starting to be used for domestic hot water. Again, this sounds very confusing, all these different options, but this is to explain that the word heat pump can actually mean a lot. Is it an air source or is it a water source heat pump? Is it heating and cooling air? Is it heating and cooling water? And this is, once you have that information, you can actually start figuring out what kind of machine you're actually looking at. Next, we'll talk about some nomenclature before we dive into these heat pumps. So a reversible chiller is usually referring to a machine that, again, the word chiller is referring to heating and cooling water. So that's usually an air to water machine, or it can also be water to water machines. You can have a reversible chiller water to water machine. Air source heat pump chiller, as the name implies, heats or cool water, so it's water to air. Heat recovery chiller, those can be air to water or water to water. VRF, variable refrigerant flow, those are air to air or water to air. Mini split or multi splits, those are air to air. Whereas a heat pump water heater, those are air to water or water to water. Sometimes you guys are going to hear the term as well, ductless, and ductless actually means it's just a type of indoor unit. I just wanted to mention that because usually it falls under mini splits or multi-split, but a lot of contractors you'll hear oftentimes they'll say, oh yeah, I do ductless. And really what they mean is, that they install mini splits or multi-split. So ductless is just a very specific kind of indoor unit that doesn't use ductwork. So we'll get into all the different kinds of indoor units, but just wanted to mention that in the nomenclature. So now we're starting to the different types of air source heat pumps. So what we're looking at here at the top is a PTAC or a package terminal AC. And these are often seen in hotels or apartments. It takes heat from the room and actually throws it outside. Some of them also come with the heat pump function. Again, the key component being that reversing valve, as we previously discussed. And then it will throw heat from outdoors and actually bring it inside. Now, these don't work down to very low temperatures. So oftentimes you'll see these with electric heat in there as well. Rooftop units can also come as heat pumps. Again, there's some issues as well with low ambient heating operation with heat pump rooftop units, but they are getting better and they are starting to be more common. If you do take an existing mall, for example, with 5 package rooftops serving a specific tenant, if they come to need replacement, you could replace them with electric air source heat pump rooftop units. There's starting to be some good options for those. Mini splits or multi splits, those are like residential or like commercial versions of air source heat pumps. Mini split is where you have a single indoor unit tied to one condenser, and a multi split is where you have multiple indoor units tied to a condenser or an outdoor unit. as it's not always a condenser. With a multi-split, each zone or each indoor unit will have its own control, but the entire system will have to be in heating or cooling. Next, we'll get into another type of air source heat pump, probably the most common commercial air source heat pump that you will find. This is probably Mike's and I's favorite topic, and we've talked about this for a long time, but what we're looking at here is each indoor unit on the right here has actually an expansion valve. It can actually adjust how much refrigerant it wants based on the load in the space. The other unit will actually in turn modulate the compressor to adjust the amount of refrigerant it's sending to all the indoor units. The other unit can also be twinned up to the 3 different modules, so they can actually become quite large, and that's all depending on the design requirement of the very specific building. We'll get into efficiencies for these types of systems a little bit, but for these types of systems are really good at part load. At full load, they're pretty good, but they really shine at part load. Now, there's actually 2 different kinds of VRF. There's actually VRF heat pump and VRF heat recovery. Heat pump systems also called switchover systems, and heat recovery is sometimes called simultaneous system. What we're looking at here is actually a VRF heat pump system, and the entire system has to be in either heating or cooling. Now, let's say the entire system is in heating. Each zone can modulate how much refrigerant it wants for its own zone, but it cannot go into cooling. It has to be in heating. Next, we'll get into VRF system with heat recovery. So with heat recovery, you can actually have different indoor units and be in different modes, essentially. So one indoor unit could be heating while another one's in cooling. There's actually an extra component here that you'll notice, and it's those branch boxes. Those branch boxes come in various different shapes and sizes, and they are essentially the traffic cop for refrigerant, and they let either liquid or gas through depending on what's required by the indoor unit. This is usually the most common type of VRF system used in commercial buildings. It does depend what type of space, what type of space it's serving, but oftentimes it's preferred by the owner or the tenant to have that flexibility to be able to go into heating or cooling. So we talked about air source VRF, but now let's talk about water source VRF systems. So instead of rejecting or absorbing heat from the air, these can actually use water. They're actually available as heat pump or heat recovery, just like air source machines. Same distribution network as air source, but the main difference is that heat sink or heat source. Since we're on the topic of VRF, we thought we would talk about some of the pros and cons of VRF. Oftentimes we see these VRF systems installed in both existing and new buildings. And oftentimes, in terms of controls, they're often integrated into a central building management system. And VRF manufacturers actually make this process quite easy by allowing control system to talk seamlessly with the VRF system. In terms of installation, refrigerant piping are quite easy to fit actually through existing buildings. So they make VRF systems actually quite ideal for retrofit applications. If you wanted to run water piping or ductwork throughout the building, that would take up a lot more space than running those smaller refrigerant pipes. Now, VRF systems also, they allow for great flexibility of the different kinds of indoor units, which Mike will go into in a little bit. But something important to remember is that with VRF systems, they are zoning systems. So if you were to tell me, hey, Alex, I have a large warehouse, can I use VRF? You might be able to, but it might not be your best option. So a package air source heat pump rooftop might be a little bit better for that if you're for that warehouse. And again, VRF is all about smaller fan coils serving smaller zones. Something else to mention with VRF is it's actually very quiet as well, as you have the compressor outdoors in the outdoor machine. So it keeps all the keeps everything kind of separated from inside to outside. And that makes it more comfortable for occupants. So next we'll get into air source, another type of air source heat pump. And this is an air source heat pump machine that heats or cool water. And it's an air-cooled heat pump chiller, also called a reversible chiller. These machines are two-pipe machines. So they either have to be all in heating or all in cooling. And so in the summer on a 95-degree day, you're going to be able to supply 44-degree water to your space. Here on the right, those are just some fan coils, for example, that would use that water to heat or cool the space, but they can also be different kinds of unit. In terms of in the wintertime, you'd be supplying 130-degree water and be getting 110-degree back from your fan coils usually. Now these can also be 4-pipe machines, so where they can actually do heating and cooling all in one machine. So they're starting to be common as well, 4-pipe air source heat pump machines. Some pros and cons of these bigger air to water heat pump machines. If you're using an air source heat pump chiller that will feed fan coils, as we previously discussed, you have to decide, does this machine need to be 2-pipe as a changeover system, or can it be 4-pipe? Does it need to be 4-pipe for simultaneous operation? In terms of advantages, this is a bit of a newer technology, but there's some advantages to going with these kinds of machines. If you have an existing hydronic infrastructure in your building, these can make a ton of sense. Instead of running your refrigerant lines everywhere, the existing hydronic infrastructure can actually be reused in some cases. These still have refrigerant inside of them, but there's actually no refrigerant throughout the building. So that's kind of another little bit of an advantage, and there's less of a chance of a leak. But they do also allow for a quicker transition to lower GWP refrigerant, which we'll talk about refrigerants in a little bit, but it's quite helpful that they have that it's all kind of dedicated into the outdoor unit for those machines. These machines can also help with domestic hot water. They can't specifically do domestic hot water, but you're making hot water in your building, which can actually help to electrify your domestic. In terms of disadvantages for these types of systems, low ambient capability. Usually, oftentimes you might still need a backup boiler for heating, and they can't really get close to what real air source heat pumps like VRF can do in terms of heating capacities and D rates for heating. And this is a bit of an issue for cold climates as we're in here. So oftentimes these need to be designed with backup heating, extra boilers, and that's a big deal. In terms of cost, generally hydronic is the most expensive option, and it's a lot more expensive than, let's say, an equivalent VRF system. Generally hydronic, if we're talking about all electric in the all electric world, it is the most expensive. In Europe, where they don't have a lot of natural gas, hydronic systems are the more expensive option compared to the split systems and VRF. Next, we will get into, I didn't talk about these water source heat pumps, but next we'll get into water source heat pumps, which are, again, these are water to air. And again, as I previously mentioned, these are the most common type of water source heat pumps machine. They do come in various different sizes and capacities. And here on the right, we see a horizontal water source heat pump. And this you would often see in a commercial office building, for example. Vertically on the rightmost would be often seen in a multi-family application. Again, here everything is in this machine. So all the compressor, condenser, evaporator, these will be connected to water to be used to reject and absorb heat through a condenser water loop. If the condenser water loop is a geothermal system, as we previously mentioned, then we call these types of heat pumps ground source heat pumps. Next, we'll get into water-to-water heat pumps. Again, this is kind of very similar to air source, but back to the question before, if you do have a geothermal system, you can actually do VRF, as you previously mentioned, but you can also run your hydronic loop through a building, as you can see here. So you go from your geothermal loop and you give hot or cold water to your space. Now on the slide, we see them as heat pump machines. So the whole machine has to be in either heating or cooling, but they can also be 6-pipe machines. So they'll do actually heating and cooling using one machine. And this machine would be connected directly to your geothermal loop. And if you're doing a geothermal system, the major kind of competing systems or options are straight water source heat pumps, where your geothermal loop runs through your entire building. And you put, if it's residential, then you put a water source heat pump in each suite, or if it's a school, you put it in every classroom. Or you could also do water source VRF, where you're running refrigerant piping throughout your building to deliver heating or cooling, which is a bit of a more expensive option, but it's more efficient. This right here on this slide is actually another option that we're actually starting to see in large schools and more commercial buildings, more complex commercial buildings, and that do want to use geothermal, but also want to use kind of central air handlers. So they'll actually deliver cold and hot water central air handlers to do heating and cooling. Now going back to air to water heat pumps for domestic hot water. Residentially, there's a few options for air source heat pumps, water heaters. They actually, some are indoors with physical heat pump modules and integrated into the hot water heater, while others are outdoors with a tank indoors. This technology is still in its infancy, and operational costs are still a bit of a concern. But down the road, as gas does become more expensive compared to electricity, we think that these will get more popular. Commercially, it's still of a emerging technology. You have all sorts of manufacturers going after this. You have the two main kinds are the big air source heat pump chiller manufacturers that can now generate domestic hot water. And there's also the VRF manufacturers that are starting to come up with solutions for this. Now we're going to talk a little bit about pricing comparison between air source and water source heat pumps, as we previously said we would get into a little bit. So on the air source side, the most cost-effective option is probably on the mini split or multi-split side, and that we usually assign that the lowest cost. And then we can get into packaged rooftops, and then there's a bit of a cost difference into exactly what you're doing as a packaged rooftop unit can be serving. Is it a packaged rooftop unit with VAV? What is it? Is it just a single zone? Or so that's where a little bit the cost difference is. Staying on the air source side, you can also go VRF, which again, the cost is a little bit dependent on what you're doing. Is it a heat pump system? Is it a heat recovery system? What type of indoor units are you using? That will all change a little bit the cost profile of that solution. Next thing on the air source, you can actually, if you do air to water heat pumps, whether that's 2-pipe or 4-pipe, again, that does change that cost profile a little bit, depending on what it's serving or what exactly the machine is doing. Now, if we flip over to water source, assuming this is geothermal, water source heat pumps would be the most cost-effective option under water source. And then you'd have water source VRF, which again, depending exactly on what you are doing in terms of heat pump or heat recovery, different kinds of indoor units, that would also change that cost profile. And then on the pricier end would be the water to water heat pump chiller machines that we talked about as well. Next, we're into refrigerants. So something important to remember is that every single kind of heat pump that's been discussed so far actually uses refrigerants. Refrigerants can contribute to global warming if they do escape the system they're in, and that if they're not reclaimed. The global warming potential of a specific refrigerant was actually developed to compare the different types of refrigerants. If gases were to escape a piece of equipment with a refrigerant with a lower GWP, it's actually not as bad for the planet as a higher GWP refrigerant. So R410A is actually currently used in all new air source heat pump and VRF in the US, with an exception, which we'll talk about in a little bit. R410A does not contribute to ozone depletion. You might remember the days of R22, that refrigerant that was phased out in the 90s and phased down in the 90s and 2000s and officially phased out as of January 2020. R22 can no longer be imported or manufactured in the US. So this was actually due to the ozone depletion of R22. Now it's still possible to buy recycled R22 that's been reclaimed or from existing equipment, or actually use drop-ins as well, like Blue-On, which is our 454A. And the phase out of R22 is actually one of the most successful global treaty that was agreed on. If we do go back to R410A for a little bit, the refrigerant itself is not too bad, but it's actually the flame retardant additives that is in the refrigerant that makes it have a high GWP. And there are actually efforts to transition into lower GWP refrigerants, which we'll get into now. By the way, some of you might be aware that the EPA actually tried to phase down refrigerants like R410A in 2015 and 2016, just like they phased down R22, but they actually got sued and lost. The premise was that the EPA did not have the authority to phase down based on global warming potential, but they were only allowed to do it based on the ozone depletion potential under the Clean Air Act. Now, this is actually where the American Innovation and Manufacturing Act, the AIM Act of 2019, was actually passed in 2020 as part of a COVID relief bill. But under this act, it actually gave the EPA the authority to phase down HFCs. It actually advised the EPA that the production and consumption of HFCs should be reduced by 85% by 2036, which actually gets us in line with the international phase down plan called the Kigali Amendment. So manufacturers need to either use some of their allowance limits. No, sorry, they need to either use recycled or use some of their allowance limits provided to them. And this actually started as of January of this year. So unfortunately, there's a bit of a loophole with anything that's not manufactured in the US. It actually doesn't fall under this. And unfortunately, this a little bit handcuffs American-based manufacturers. And that loophole is currently being looked into. One of the issues today is that the building codes actually do not allow the prime alternative for R410A yet if the refrigerant goes to occupied space. And this prime alternative for high pressure applications is R32. I do mention high pressure because if you do look at a water-cooled, cooling-only chiller, it's actually easier to get lower GWP refrigerants as these are low and medium pressure refrigerants. Now, when you're trying to do heating, this is really where high pressure refrigerants come into play and where they're really important. But currently, again, you cannot have R32 through occupied space, and it's going to be quite a few years before that's allowed and at the federal level, and then a year or two to get adopted by the different states. Our estimate is that we're probably still 5 or 6 years away from seeing R32 in Vrf systems and larger source heat pump systems. Now, R32 is already started for small split systems for residential applications. And again, as I previously mentioned, air source heat pump chillers can transition quicker to this next generation refrigerant than Vrf, as previously mentioned, as everything's kind of centralized in the outdoor machine. There's actually with R410A, there's actually no, or with any refrigerant for that matter, there's actually no global warming if it actually stays inside the machine it's serving. There's no environmental risk with refrigerants as long as everything's contained in that system. So how do you actually minimize the impact of refrigerants on the environment? Proper install procedures actually play a large part in this, and actually an afterlife program as well for refrigerants will help as well to allow a kind of a recovery of refrigerants into the economy of refrigerants, and be able to be reused on another heat pump technology that will help reduce environmental impact. Again, after all, the environmental benefits of using heat pump technologies actually outweighs the impact and potential chance for a leak. Fear not, R410A is not going away soon. All these systems for the foreseeable future will be in R410A. It will continue to be available for the next few decades, just like R22 was available for a few decades for service of existing equipment. We're excited about the arrival of R32 as a next generation refrigerant, as it can have higher efficiencies and lower GWP and just overall less of it. But in the meanwhile, R410A systems they're safe, and they're safe to install and go through their life with no problem. And we just have to focus on quality install and keeping the refrigerant inside of them. Next, I'll pass it over to Mike to talk to us about efficiencies.
Thanks a lot, Alex. Just getting the mouse control here. Just bear with me, everyone. Okay, looks like I got it. All right, so now we're just going to break down the advantages of having an inverter-driven compressor. That's the type of compressor we're utilizing on heat pump technology. It allows for variable speed on that compressor. So first off, I'm going to talk about conventional speed compressors. These are single speed compressors. It's either fully on or fully off in operation. So I most liken this to, for anyone who's walked a dog before, if you are not quite in control of the situation, the dog is ultimately leading you in that walk. Well, in this situation, we're kind of allowing the temperature of the space to guide what the system is doing, as opposed to the system guiding the temperature of the space. In this particular example, we have a compressor that is turned on in order for the indoor space, which starts at 90 degrees, to start to cool. We want that to get that 90 degrees down to the set point of 75 degrees. So the compressor will come on. It is going to lower the temperature within the space. And as soon as it overshoots, it's aiming for 75 degrees. It's going to overshoot a little down to 73. We're going to turn that off. That's going to temperature in the space is going to rise all the way up again, up to 77. It's going to turn back on, and we're going to have a pretty wide range here that we're actually going to be feeling in that interior space, from 73 to 77 degrees. Now, that's ultimately why I'm saying you're letting the dog walk you on this walk, as opposed to being in control of the situation. I'm going to contrast that now with a variable speed compressor. We're going to start off in the same situation. We're starting at 90 degrees, where we're going to bring the system on. So the compressor turns on, we're going to lower that temperature, and instead of just outright turning off the compressor for this system, it's instead going to ramp down. So that's where that variable speed comes into play. So if we're able to ramp down the compressor speed, we're going to have a much, much tighter deadband around that 75-degree set point. So this is going to be you in control of this walk, and the dog is walking along with you. You're in control of the temperature of the space. You're not reacting to massive, massive fluctuations in the temperatures in the conventional speed systems. So we're talking about efficiency when we're talking about, the advantages of the inverter-driven compressor. So when we're talking about cooling efficiency, there are a number of metrics that we use to assess energy efficiency. One thing we utilize is EER, or energy efficiency ratio. It's a very simple formula where you measure the cooling output in BTUs, and you measure that against the total electricity in watt hours that you're putting into the system. BTUs are a unit of energy, electricity input in a measure of energy. And by using that, you're going to figure out what your ratio of your output to your input is at a given time. But so this one measures the efficiency at a peak load situation. So it's going to measure your total cooling output at the absolute max cooling load necessary. So, but the thing with this is that your system is only going to be seeing a peak load less than 1% of the time. That's going to be the peak time of the summer months, where it's the absolute hottest, where every single indoor unit in your system is calling for full cooling at the same time. That's not a very common occurrence in the lifetime of a system, so that's not exactly the best metric to actually assess the efficiency of that system. Another metric we can utilize is the Integrated Energy Efficiency Rating, the IEER. That's going to take the weighted average of various EER values at different temperatures to represent the performance of the system over the course of the entire year. So it's going to take a look at that middle of the summer cooling efficiency. It's also going to look at the shoulder seasons. It's going to look at what's going on in the fall and the spring. It's also going to take a look at any cooling operation you may need in the winter. There are absolutely cooling zones that are going to exist in the winter months. If you have equipment in the space in one of your zones, you're definitely going to need to extract heat from that space in order to keep the equipment at safe temperature levels. Now, in heating, we have similar metrics that measure the performance of the system. One of these would be COP, coefficient of performance. Very similar metric. It analyzes energy that you get out of the system divided by the energy that you need to put into the system. So, for example, if you're thinking of electric resistance heat, that's your baseboard with an electric resistance coil running through it. That's effectively a COP of 1. Actually, it's a little bit less than 1 because you're going to get some losses in that system. So it's about a 0.98 COP. Now, next slide, I'm going to get into the advantages of heat pump, but with the heat pump technology, you're actually able to get a COP of greater than 1. I'll discuss that in a minute. Alex touched on that a little bit later. The fact that we're not generating heat, we're transferring heat. So if we're able to move heat from one location to another, we're not generating that heat. We're not burning gas, we're not burning oil in order to get heat. We're taking it from somewhere and moving it elsewhere. It's a much more efficient way of getting heating BTUs. So in terms of COP efficiency publications, COP is oftentimes measured for performance at 47 degrees and 17 degrees, which is just a way of taking a look at what does a heating output look like in your shoulder season months, maybe your April months in the New England weather, or hopefully we're getting there sooner than then for 47 degrees. But you're also looking at 17 degrees, a very common wintertime heating temperatures. Now, you can calculate COP values for other temperatures as well. If you're curious of what your COP is going to be at 0 degrees, perfectly fine. You would just need to go into your respective manufacturer's engineering manual and take their published information and do that manual calculation. Now, smaller equipment, these would be more your mini splits and your multi splits. They also publish heating efficiencies in what's called HSPF, or the heating seasonal performance factor. That's a metric that's used as well to differentiate between like heat pump models for smaller heat pump systems. Again, that's mostly going to be in single phase equipment, residential or light commercial. So here's a chart just breaking down what a COP looks like for various different types of systems. And as said previously, electric resistance heat is a COP of approximately 1. It's going to be a little bit less than 1 because of those losses. Your gas-fired furnace or gas-fired boiler, that's going to see a COP of 0.85 to 0.99. If you have a 95% efficient gas boiler, that's what that is talking about in terms of efficiency. It's COP. So it's going to be burning a certain amount of gas or oil or whatever your fossil fuel driven heat source is. And you're going to be getting out a little bit less than that just because of losses in the system. With a heat pump, you're actually able to achieve COPs over 2. In fact, oftentimes throughout the year, greater than 3 or even approaching 4. And this, again, is because we're not generating this heat. We're powering our system or powering our compressor to be able to cycle refrigerant throughout a system. If you have a system that has a heat recovery component, we'll be getting into that a little bit more in a bit, but that offers the ability to transfer heat from a zone that is in cooling to another zone that's calling for heating that's on the single refrigerant network. So if that means we have all this equipment in a server room and it's getting really, really hot in there, there's so much heat that we need to get out, extract, and cool the space. If that's on a heat recovery system with other zones, that's maybe just the general office area, that zone requires heating. Well, instead of ejecting all the heat we're removing from the server room to the atmosphere outside, we're instead going to transfer that to another zone that requires that heat. So that way we don't need to extract any more heat from the exterior space. So we're drastically improving the efficiencies of our heat pump system. So when we're talking about how systems operate in cold weather, there has absolutely been, fortunately over time, it's gone down quite a bit. But when I first entered the heat pump industry about 6 years ago, there was absolutely still a lingering sentiment that heat pumps could not possibly heat in the New England climate. And this was certainly a thought process or a mindset that stayed over from previous generations of heat pump equipment that didn't have the robust technology necessary to extract heat at those colder temperatures. But with that said, we have had various advancements in heat pump technology over the past decade to the point now where all manufacturers effectively have their cold climate model series for their heat pump equipment. Daikin has their Aurora series, Mitsubishi has our Hyperheat line of equipment. Effectively, all of these are flash injector, vapor injection technology for our compressors. This is an improvement that allows for additional ability to extract heat from outside air, even temperatures below -10 degrees. Between Daikin and Mitsubishi, who's represented on this call, we have published data for our outdoor equipment down below -20 degrees. That's not exactly a temperature we're going to see often in New England. In fact, it'd be very concerning if overnight we saw lows 20 degrees below what we typically see. But nonetheless, the equipment that we sell is capable of extracting heat from that air even as low as -20 or even further. With that case, even with those low temperatures, a question that may be asked is, okay, well, what is your COP? What's the efficiencies at those cold temperatures? And that's an excellent question, because we definitely are going to have derates associated with our equipment as the temperature outside goes down. So as the temperature outside goes down, the compressor is going to have to work harder in order to extract that heat. But even below 0 degrees, we're still achieving COPs over 2, even below 0 degrees. So in that question, like, is a gas-fired boiler going to be more efficient at that temperature? Well, I don't know. From an energy efficiency standpoint, it wouldn't be. We would still get more efficiency out of the heat pump. That's a question where I would just challenge you to take a look at your utilities. What is the gas rate versus the electric rate? So at that point, you could perform that cost-benefit analysis to see at what temperature would those particular technologies be more advantageous. Now, further, in cold weather, we no longer require backup heat for air source heat pump equipment. That this in previous generations, when our equipment lagged behind as temperatures approach 0 degrees, that's not the case anymore. We have VRF or heat pumps as a whole as the sole sources of heat for entire buildings. But with that said, we do have fully functional and efficient legacy fossil fuel driven systems that are out there. And building owners oftentimes want that to be integrated into their VRF or heat pump systems. That's perfectly fine. We do that every single day. There's no use in ripping out a boiler system that's 10 years old if it's functioning perfectly fine. Great, let's keep it in there and let's stage the equipment so that that boiler doesn't need to kick on until it gets 10 degrees or below outside, because maybe once it's 10 degrees, it's more cost effective to switch over to natural gas or oil. And you could take a look at your own utility bills and you could find out that exact case. But Regardless, if you have that legacy system on site, we're more than able to tie it in with that existing system. In addition, ground source heat pump, if we're talking about water source equipment, this is not air source equipment, water source side, ground source heat pumps will even further avoid any derates associated with cold ambient conditions by utilizing steady temperatures of groundwater underground. That's going to have very, very little deviation over the course of the year for that groundwater supply. So that effectively eliminates any derates associated with winter conditions. So we're going to talk about now of the various ways that, that we use heat pumps in order to and efficiently design systems to avoid any of those heating derates. Again, as it gets colder outside, the performance of the system is going to slowly start to diminish. So here are the methods that we use to mitigate that, to make sure that even in the worst case scenario day, if you have a VRF system as your sole source of heat, we'll make sure to design it in such a way that you get all the heat you need in the worst case scenario. So the different ways that we approach this are as follows. The flash or vapor injection technology that has allowed for more extended heating temperatures that we can operate in, tying in those auxiliary heat sources, how to design VRF as the sole source. If you want to install your outdoor units inside, that's a way of actually avoiding some derates as well as water source, just eliminating the ambient conditions altogether. So first off, I want to talk about our flash or vapor injection technology. Again, just going back to the proprietary terms, Mitsubishi has our hyperheat equipment, Daikin has the Aurora line of equipment. Those are the cold climate technology series of equipment that allows for extended performance in cold temperatures. And how this occurs is that with previous generations of equipment that didn't have this technology, when temperatures got so cold outside, the compressor needed to speed up to get to 100% speed, and it would just be running and running and running to the point it would start to overheat because it was running so fast for so long. And with that, there came a safety switch that just triggered in the system, cut it off, and made sure that your compressor didn't overheat, and the system needed to have downtime. Now, that was eliminated with the invention of flash or vapor injection technology. What this does, it has a separate refrigerant circuit whose entire purpose is to cool that compressor when it overheats in those cold climate situations. So by adding that liquid refrigerant to that compressor, we don't need to worry about it overheating, so it can operate at a higher speed for longer periods of time without any worry of any safety issues. This allows the system to perform at temperatures below -22 degrees. We get 100% of our heating capacity down to 0 degrees. That means no derates whatsoever. That means that at 0 degrees, the system is operating the same it's operating at 40 degrees. But with this also, we could get even up to 85% of heating capacity down to -13 degrees. And if we're talking about the New England climate, if we're looking at -13 degrees, that's an extreme temperature that, unless you're talking about the northernmost parts of Maine, New Hampshire, Vermont, and we certainly have installations there as well. So please don't rule out heat pumps or VRF in those climates. But even in those climates, our systems are going to have very, very minimal derates associated with them. Now, another way that we prepared for operation in cold weather is tying in with an auxiliary heat system. And this could be, a radiant system, electric resistance heat. If you have district heating where you have hot water serving an entire campus, we could absolutely stage that as well. Now, the way that we approach this is that we first want to determine the primary and second stages. The reality is we want our VRF, our heat pump equipment, to be the primary stage. It is a high efficiency system. You're spending the money for that high efficiency system. It should be operating as its primary stage. And the second stage should be picking up where the VRF system may fall short, or you may programmatically change it in such a way that the second stage would kick in at certain temperatures. Now, What are those energizing methods? Space temperature drop. So if you just if you're seeing in a space that the in one particular office, the set point is set at 70 degrees, but the VRF system is unable to keep up and it's only able to keep at 67, well, then that's going to just trigger and cause that backup system to kick on to pick up where you're falling short in those 3 degrees. And as soon as the temperature in the space has achieved set point, it'll then turn off that backup and stage it accordingly. Alternatively, you could energize it based on outdoor temperature. If you determine based on your own utility pricing that it would be more cost effective to switch over to a fossil fuel driven heating system below 5 degrees, that's absolutely fine. And we can program our systems accordingly to alternate to a second stage or alternate altogether, just trigger that second stage of heat accordingly as soon as it reaches those temperatures. But the one point I do want to emphasize is that if you size your VRF system accordingly, if you size it based on the design parameters that are given, that's seriously going to limit the actual need for that auxiliary heat system. We have dozens of installations across New England that have been designed with an auxiliary heat system that has never turned on. It's there, it's ready and waiting for the day it needs to turn on, but just based on the size of the VRF, based on the capabilities of that system, it was never really needed to turn on. So here's a decision tree of just how we would go down the process of determining what type of auxiliary heat, how we would integrate auxiliary heat into our systems. We would first ask the question, is there an existing system available? If not, well, then you're going to have to size that VRF system as the sole source of heat. You're going to want to accommodate for any D rates you may see in that particular climate and size the system accordingly. If you do have auxiliary heat, great. How is the system set up? Is it a district heating infrastructure? Is it a campus style with just a single, hot water piping running through every single building, and it's there, it's going to be turning on, there's no way of turning it off, it's running through that radiator? Well, if that's the case, there's very little we could do to stage it because it's still running through that radiator. So in that instance, we should use the district heating as the first stage of heat and stage your VRF as backup. Have the VRF serve as picking up wherever the district heat is unable to achieve. If you don't have a district heating infrastructure, if you have individually zoned auxiliary sources, like radiant baseboard loops, electric baseboard loops, etc., there we would want to stage the VRF as the primary stage and have that auxiliary heat source be the backup, the second stage. All right, so I've pulled some information from our engineering manual just to showcase how we go about sizing a VRF system for its particular climate. So what I have here on the bottom right, here are the capacity D rate charts for one of our systems. It's the ratio of your heating capacity based on the temperature outside. So I'm going to start and look at this from a perspective of a Boston design temperature. At Boston design temperature, which is 6 degrees Fahrenheit dry bulb, we're going to be looking at this red line right here that's running to the bottom. So that's going to be at the 6 degree line that runs up. And what capacity are we getting at 6 degrees? We're getting over 100% of our capacity. And the reason we're getting that is because of the flash injection technology that we previously mentioned. That's going to give you more robust heating performance in cold temperatures. So for a system that has over 100% of its heating capacity at design day conditions, you can size that system without really worrying about the D rates associated with it, because on a design day condition, you're going to have more than enough capacity to serve all of your indoor unit fan coils. Let's contrast that with a Burlington, Vermont scenario. Burlington, Vermont, the design day is -12 degrees. Well, -12 degrees, we go on up. our system is only going to be seeing about 85, 86% of its heating capacity at the design day. That's not that big of a D rate, but it's certainly a D rate we want to consider. So in our respective design softwares, we're going to be running the built-in simulation software that determines the output at each fan coil. If we find that our system, if the D rate that our system is seeing is too much for that given climate, we're going to upsize our outdoor unit. If we're not going to be able to output as the sole source of heat on design day conditions, we're going to want to make sure our outdoor unit has more capacity. So effectively, when you're sizing a sole source of heating VRF system, you're going to be taking into account ASHRAE design conditions. You want to make sure that on design day conditions, you have enough heat output from your system to comfortably heat the space. And we're going to make sure to account for a diversified building load. We're not going to take a look at this as every single zone in the whole building is calling for full heating at once. If you have an office building with a conference room, if that conference room is fully occupied, that means that there's going to be other zones throughout the building that are unoccupied just by the nature and occupancy of the various zones. We are going to take that into account to make sure that at any given moment over the course of the day and any time of year, you're going to have your desired output. It's a little bit long-winded, and I apologize if things got confusing there. I'm more than happy to answer questions later on, but I'm just going to move forward for the moment and talk about some other methods that we can design around cold weather. So another way that we can eliminate the D rates we would see on cold weather days is to actually install your outdoor units indoors. So here's an example. Here's a picture of a VRF outdoor unit. I'm using outdoor unit in air quotes there because it's inside. For this particular instance, here's a schematic overview of what this would look like, where we have a gas unit heater in the space that's going to be tempering the air. So the outdoor unit, it's not going to be seeing 0 degrees when it's 0 degrees outside. If you have a gas unit heater set up in here, set to 40 degrees, well, that outdoor unit is only ever going to see mild heating conditions over the course of the year. You're going to mitigate the D rates associated with that unit in that particular climate. This particular configuration greatly simplifies service and maintenance. Your contractor, he's going to be thanking you if he has the luxury of working in a covered heated space in the dead of winter. And this is also a very useful tactic if you're working in urban environments, high-rise environments where there's very limited rooftop space. You can actually put this equipment indoors through louvered walls on the side of a building and potentially have your condensing unit module on each floor. So this way you're not utilizing your rooftop space. You're potentially freeing up rooftop space for PV solar arrays effectively. So here's just various considerations as well. All right, now when it comes to maintenance, I definitely don't want to forget about this. Heat pumps, they operate well when they're, I'm just going to read this verbatim because it bears repeating. Heat pumps operate well with proper system design, installation, programming, and maintenance. The way that all manufacturers' warranties work for heat pump technology and heat pump systems and VRF systems is that we want to make sure that the person who designed the system is trained up and understands how the system is designed. We want to make sure the person who installs the system is also trained up and knows how to properly install the equipment. And lastly, we want to verify that the installation as it's installed matches the design. If you meet all those three things, you're not going to have to worry about the potential for a refrigerant leak. If everything was designed correctly, if it was installed correctly, and we nitrogen purged in all of our brazed joints, and we don't need to worry about corrosion, well, that's going to mitigate the need for maintenance down the line. But with that said, there is maintenance associated with heat pump system. I certainly don't want to forget about that. We are going to require to check, clean, and replace indoor unit filters regularly. It is an HVAC system. There's going to have filters inside it. Please make sure to change them regularly. Going to want to make sure your outdoor units are free of debris, and certainly want to make sure they're designed above the snow line. We recommend designing equipment to be on 18-inch stands well above the snow line, so snow doesn't build up along the sides of it. That's going to severely impact the ability to extract or pull heat out of the air. We want to make sure that condensate removal systems are properly maintained and nothing is corroding and we don't have condensate dripping all over the place. Definitely a major consideration as well. But ultimately, just something to consider. Heat pumps, as much as a great install and a great design is going to seriously limit the need for your service contractor to come back and address problems, there are still going to be traditional conventional maintenance that takes place. All right, so at this point, all right, so now it's a good time. We'll now at this point, we're going to go through the different types of options associated with, your outdoor units, the various indoor unit options we have to work with, as well as how ventilation ties into all of this. So first and foremost, I just want to further drive home the difference. We have multi-split systems, multi-split heat pump systems on the left here. Here, just examples, your VRF systems, air source heat pumps, ground source heat pumps. These are all one type of system. Mini splits are another. Mini splits are more so we're talking about one-to-one types of systems. Again, multi-split is different from VRF as well, just based on where the expansion valve is located in the system. But ultimately, we're going to break this down right now. Mini splits, which is single zone, and VRF and multi-splits, which is multi-zone. Now, on the various indoor units we could choose from, we have our wall-mounted equipment, and all these fan coil types are pretty much common across the board across manufacturers. Your wall-mounted unit is typically going to be the cheapest option of all heat pump fan coils, just based on its size, based on just its appearance. Typically, ductless units are going to be cheaper than ducted units, and that's just the nature of how it goes. These units are going to require a separate condensate pump for condensate removal. In addition, we have ceiling suspended units. So these are actually going to be located under the ceiling. These have a good deal of throw to them, so they could actually reach the opposite side of a long, narrow corridor potentially. We also see these fairly often in school settings. We have floor standing units. These are great swap outs for any existing radiators that may exist in the space. These are available in both an exposed and a concealed setting. The exposed here is just showing it has an aesthetic plastic exterior, but we also have one that could be built into a wall or built into millwork potentially. We see that actually oftentimes in churches. So right underneath where the stained glass windows would be, built into the wooden millwork on the sides, we would build in these floor standing units to blow heat up from the sides. Here's an example of exactly that concealed version, just how these are built into the sides. Oftentimes in churches, we have very high ceilings. So putting fan coil equipment at the ceiling level and delivering heat downwards isn't exactly the most efficient way of delivering it to the space. So the best we have to work with is oftentimes the perimeter. And of course, now we're going to our ducted style units. And a lot of people, when they think heat pumps and they think VRF, they think excuse me, they think ductless. They're like, well, it's only refrigerant. We're not having air duct from the roof. This is a ductless system. The reality is the majority of fan coils that we're actually selling are going to be ducted units. And in fact, the most common style are the medium static ducted units, a very versatile unit that can go in conventional style ductwork applications. It's the only difference is it's being served by a refrigerant circuit as opposed to air ducts all the way to the roof. And this equipment, it comes in various static settings. We have our low profile ducted units. Those are oftentimes a great fit for those hotel rooms with very limited above ceiling space right above the door. Those low profile units can fit right in that entryway space, and that would serve an entire unit. If you have medium and high static ducted units as well, static up to about just under an inch of static for those high static situations where you just have one single unit serving a very, very long length of ductwork. That's an option as well. Yep, here's an example of such a high static unit, and just showcases just how much ductwork we could put off of one of these units. And certainly the vertical, or rather multi-positional style ducted unit. This is very common in apartments or condo complexes, especially in retrofit applications where there is an existing vertical stack style fan coil, and we want to minimize the amount of rework we're doing to the space. This will fit directly into those types of box outs. It will fit directly into the closet space, and they have minimal clearance to the side, so full service access directly to the front. And these units as well are also available with electric heat kits as well for any particular circumstance where you want to have emergency backup heating built into your system for any heating pickups you may need to achieve. We also have the cassettes, the one-way cassette here. Again, it's shooting the air one way, very narrow profile. On smaller systems, this equipment is actually designed to fit in between joists. Larger equipment, if I'm not mistaken, it tends to be larger than that, but especially for residential applications, there are solutions for one-way cassettes that actually fit directly between joists. And there's also cassettes where you have 2x2, which fits directly into a standard 2x2 ceiling tile, as well as a 3x3, which certainly offers larger tonnages, but it also has additional features such as a 3D infrared camera that scans the space and does spot heating and cooling based on the detected thermal conditions of the space. If it will know if a person is sitting in a particular seat, so it's not going to blow the air directly on them. It'll blow towards them if they need the heat or the cooling. So it's a very comfortable way of delivering heating and cooling to a common area space. Now, when it comes to ventilation, we need to remember that all buildings require fresh air ventilation, especially if we're talking about on the commercial end of the spectrum. Now, many buildings, they depend on windows or just standard passive air leakage to handle their full ventilation loads. This is not an efficient way of delivering ventilation to a space. It's, again, passive, the way it's saying. And it's also, it doesn't ensure air quality. There's no metric for CO2 levels that to deliver that fresh air. And there's ultimately no guarantee you're going to have a well-distributed fresh air load throughout a space if you're just depending on windows. The central zones of the building, they're not so lucky to have the windows potentially that are on the perimeter spaces. But with that said, ventilation, there are a number of accessories that, especially in light of global events as of late, that integrate with our equipment to minimize virus transmission. Filtration, depending on the fan coil type, you can have MERV filtration up to MERV 13 in some instances. UVC lights, that definitely could be built into the ductwork as well in order to neutralize any mold, virus, et cetera, in air. I will just say for those in the crowd, just, if anyone else like me has sat through a great number of these different types of presentations over the past 2 years, one thing I've learned about UVC light, if you could see it with your own 2 eyes, it's not working because that will damage your eyes. That needs to be built into the ductwork. So one thing I've personally learned on UVC light integration. And lastly, bipolar ionization, another high-tech method of neutralizing any contaminants in the air as well. That's another element we can build into our designs. So It's important to note most heat pumps, they're designed to only provide heating and cooling to the system, just heating and cooling. That's the H and the AC in HVAC. Additional equipment is typically necessary for that ventilation aspect. And that's typically done in the form of a dedicated outside air system or a DOAS system. So we certainly want to take a look at the existing infrastructure, the layout of the building in order to determine how we're going to integrate ventilation with our equipment. Sometimes we're able to have direct ducting straight to our equipment with an induct heater directly from outside, and that's all the ventilation we would need. Other times we'll utilize just a whole ventilation system that has ductwork laid throughout the building that delivers ductwork separately to a space or integrates with the VRF equipment to deliver a mix of fresh and recirculated air to the space. So we would, with that, we want to consider energy recovery in order to heighten system efficiency. That would be utilizing the waste heat that we're going to be exhausting from the building in order to preheat the incoming air from the outside so that the DOAS system isn't going to have to pick it up from 10 degrees to 70. It would only need to be 10 degrees to 40, and the rest delivered to neutral air would be through an energy recovery system. But in addition, DOAS systems can also provide dehumidification that heat pump systems alone are not sized to meet. So if you have a dehumidification heavy type of application, I would caution to not just assume that heat pump that'll be able to do it. Certainly we could tie in, and certainly we want to take a look at that application. But the equipment as designed wasn't meant strictly for large dehumidification loads. So we will want to take a look at that in a nuanced way to ensure that we deliver the air requirements to the space. And lastly, and this is an important note, in another way of how we design in cold climates, is that an option to offset the heating load in order to allow your VRF system to be the lowest tonnage possible is to oversize your DOAS system. So what that would mean is that if your DOAS system is oversized, it's more than enough to provide that heated outside ventilation air to the space. Because you're getting a great deal of heat from your DOAS system, your heat pump system, we're not going to have to worry as much about those D rates in the absolute coldest parts of the year, because your DOAS would then be used to pick up whatever D rates that your heat pump system may not be being able to pick up. So that's an option that we consider when we're taking a look at the whole of a building's HVAC system and to how we could size it accordingly. All right, so at this point, I'm actually going to be turning it back over to Alex. Alex, let me just give up this remote control. And at this point, yeah, Alex, please feel free to get started. I see a bunch of questions in the queue here. I'll do my best to power on through these, but if I don't get to your question in time, we'll definitely take time at the end to go through these in detail.
Absolutely. I was looking at some of those as well. Some good questions. Keep asking them. So we talked a little bit about this, but how do we actually decide between our air source and water source? So oftentimes the water source option tends to be a little bit more expensive, but does tend to perform slightly better. Actually, not as much as you think, but it is a bit better than air source in terms of operational costs, as you're rejecting absorbing heat from a more consistent source in the ground. Now, here's some question to actually ask. If you have an existing building, does it have any access to a geothermal loop? If you're looking at a downtown Boston building, there's a chance that this is not even an option. Now, don't forget the terms water source heat pump actually often gets referred to for the typical system that is used for a downtown Boston 10-story apartment building, where every suite has a water source heat pump that's being fed from a gas-fired boiler and a cooling tower. But for an all-electric building, it actually needs to be geothermal. The loop needs to be geothermal. And that's where the higher capital cost actually comes into play. Now, in terms of retrofit applications, again, this slide is kind of trying to cover a huge array of different possibilities, but we're kind of trying to simplify it. For example, if you have an existing building with a huge air handler with gas, heat, or hot water from a boiler, in that case, you'd be forced air, where the option to electrify it is using refrigerant-based systems such as water to air or air to water systems, air to air systems. But again, if you have an existing hydronic distribution loop, there are ways to actually electrify this, as we discussed, using water-cooled or air-cooled chillers, as we talked about a little bit before. Now, if you do have steam in your building, you could do electric baseboard for heating, but usually these buildings only have heating, so you're starting from scratch if you're trying to really add cooling in there. We did see a question about whether some of these types of ductwork would have to be resized if, I don't know if you answered that, Mike, but for some of these ductwork would have to be resized if you're trying to retrofit an existing building. And actually, it depends a little bit what kind of building you're looking at, but we've seen applications where it was a gas-fired unit that was kind of doing the whole heating for the whole building, and we actually retrofitted that existing air handler and used all the existing ductwork. And essentially, it's now a fully driven air source machine. It's still an air handler, but it's using a coil, using an air source heat pump coil tied to an air source heat pump machine on the roof. And essentially, it cools and heats the whole building, and it uses all the existing ductwork. So it does depend a little bit what kind of buildings we're looking at, because sometimes it is possible to do that. Now, in terms of comfort heating and cooling applications, how do you actually decide what you want? It actually all starts with the zoning. Remember, VRF and split systems are zoning systems. So, for example, if you have a gym, a central air source heat pump rooftop package unit would be a little bit of a better option over VRF system. Now, if zoning is required, how many zones? For a small number of zones, split systems might do, but VRF might be a better option for a larger number of zones. Another question to ask in Massachusetts would be whether tenant billing is required, tenant metering is required. So in Massachusetts, for a residential rental building, you're actually not allowed to meter VRF and charge tenants. So one-to-one split systems are a bit of a better option, and we actually see a lot of developers going that way as one-to-one for the rental market. So hey, one thing with these heat pumps is we love them. They're great. We think it's the most efficient way to deliver BTU to spaces, but they do work best when combined with good envelopes. And the first part of a building you should try to fix is your envelope, and you can look at improving your heat pump or adding a heat pump. In terms of cost, 5 or 10 years ago, there were some alternatives that were actually much cheaper, such as gas-fired furnaces or electric baseboard. And actually, that gave VRF the reputation of being quite expensive. That has actually changed. We've seen the price of VRF come down quite a bit over the past 10 years or so. And there's actually a lot of it going on, and a lot more trained contractors that are very comfortable with this technology. So if you do want an all-electric building or a low-carbon building, the alternatives are at, if not more expensive than doing VRF. Next, Mike will actually come back and go into some applications where both air source and water source heat pumps are used. Mike.
Sorry about that, Alex. I was in the middle of answering one of these questions.
All good.
All righty. Okay, so here's an example that I want. This is going to be giving us an opportunity to see what it's like when we walk into a building and the types of questions that we ask to get to know a project before we even talk about heat pumps in general, or rather, even what type of heat pump we're looking at. So for a multifamily application, and this could really be applied to a lot of similar types of buildings, multifamily, this could certainly be a dorm room type of setup, could certainly be an office setup where it's just multi-zone and simultaneous heating and cooling throughout the space. But in terms of design considerations, one of the first questions that we're going to be asking is, who is going to be paying the utilities for this particular project? Is it going to be the building owner, or is it going to be the individual tenants? At the moment, just with we're in a period right now where we're waiting for local law in Massachusetts to be amended in order to allow for more seamless individual tenant billing. But until that point, we want to make sure that, because this ultimately will make things drastically easier down the line. If the owner is going to be paying all the utilities, then there's going to be no issue really with having a central plant or condensed unit design serving multiple different spaces. But if the tenants are all going to be paying their bills individually, a simplified way of approaching this may simply be having single mini splits serving each space, or having multi-splits serving the spaces for each individual tenant. And separating it out like that would ultimately make the billing process significantly easier down the line. Another question we'd have, what type of power do we have? Single phase or three-phase power? If we have single phase power, well, we need to look at our mini split or multi-split or single phase VRF as our only options. We don't have our commercial grade three-phase VRF available. So we would be specifically looking at mini splits, one-to-one systems, multi-splits for a maximum of about 8 fan coils attached, or single phase VRF, which has about, if I'm not mistaken, about 12 fan coils is the maximum you can connect. Three-phase equipment, you're talking about a much, much more robust system where you could have dozens of fan coils all attached to one single condenser unit. Heat pump versus heat recovery. Are we going to want simultaneous heating and cooling throughout a space? Sometimes the question comes up that yeah, I would it's a multifamily apartment complex. I would like to have all my tenants have the ability to independently choose heating and cooling, but maybe it's a low-income housing and budgeting is an issue, and they don't quite have the finances for a heat recovery system that will allow for simultaneous heating and cooling. It's not a major buyout, but it is certainly a cost premium associated with it in the range of 15 to 20% to allow for that simultaneous heating and cooling. So that's a question that would certainly determine which direction we go. What types of space constraints do we have in the space? Is there limited above ceiling space that would really limit our ability to run ductwork in the space? Does that mean that we are essentially forced to have ductless units located within the actual occupied space, whether that's wall mount, a floor mount equipment, the ceiling suspended, or cassettes? And here's an important one that oftentimes gets overlooked: ownership. Are these condos? Are with owners of the condos? Are these apartments? Where people are just renting? Are these apartments now, but one day they may be condos? That's important to know, because when changing ownership of an HVAC system, if you own a condo with just one fan coil attached to a centralized condensed unit that serves the whole building, any changes to that HVAC system, it's officially going to require buy-in from everyone in the condo association. But if you're a condo owner and you have a split system, one outdoor unit that's yours and one indoor unit that's yours, you can make those adjustments pretty seamlessly. So that's definitely a consideration to take into account. Footprint minimization. Do we have limited space on the rooftop? Or if it's like a high rise, for example, that we don't really have a lot of footprint there. If it's the building owner wants to incorporate solar PV array into their building, it's going on the roof and they don't have any space for condensed units. That's fine. That's perfectly fine. But that's definitely going to force our hand one way or another. Potentially, we may look at mounting split equipment on the side of the building. Because it's much smaller, less weight requirements, and we can mount everything on the side of a building, especially if it's out of sight of any roadway or common walk paths. if aesthetics are an issue on that. From a footprint standpoint, that could also apply to the indoor units. Do you have an existing vertical stack fan coil in a closet that we want to minimize any rework? All right, let's rip that out. Let's put our multi-position ducted air handlers in there. And that's it. That's the indoor unit swap. That's all you need. So definitely going to want to assess the conditions of the space and what, how much space we have to work with and what are the desired minimizations of footprint that we have. And controls. This is a big one. Well, what already exists on site? Do you have a BMS? Is it BACnet compatible? Do you have auxiliary heat tied in this building? And do you want that to be tied into the VRF or heat pump system, or are you planning on ripping that out? Do you have third-party thermostats? Right? Do you have Nest or Honeywell thermostats that you want to that your tenants are all big fans of and they want that to operate their HVAC equipment? This is all possible. It's all definitely things that we could work with. But these are our day one questions, the first things that we're going to ask before we even start talking about model numbers. All right, next up, I have, here's a discussion of the various considerations we would have for water source equipment. So for the most part, we've been talking about air source equipment. That's where we have our condense units. They're located outside, or they're located potentially in a doghouse, a mechanical room. And just to clarify, because I saw one question on the subject matter, if you're placing your condense units indoors, you need to duct off the top of the condense unit and exhaust all the heat that's being rejected from the system. And you're also going to need intake louvers in that space in order to deliver fresh air over that coil. So just as an aside, because I saw a clarifying question on that. But for this, we're talking about water source equipment, where we're not absorbing or rejecting heat from the outside air. Instead, we're going to be absorbing and rejecting it from a water loop. So in this instance, we have two different water source heat pump systems. One of them is serving the left side of this building, the other is serving the right side. So some advantages you could get from a water source VRF is that you don't need to worry about your any D rates due to ambient conditions. We're rejecting or absorbing heat from a water loop. That's just going to be circulating water. It's, you know, and our systems can operate in a wide range of temperatures, 23 to 113 degrees. So we're not really seeing those substantial D rates that some air source equipment may experience. They're incredibly compact. The water source units can actually fit directly into a closet. So if you want to serve water source heat pumps on a per floor basis, that's perfectly fine. You just have this in the water closet where it's just running by this common water loop. And it's also modular, a modular footprint. You could stack these. So if the tonnage requires two of these serving a floor, that's fine. In that closet with no side clearance necessary, full service access from the front, you could have two of these, one right on top of the other, serving that space. Now here's this next bullet point is an interesting one. Now with heat recovery systems, the advantage that you get from a heat recovery system is that for zones that are in cooling mode, you can utilize that heat and send it elsewhere in that refrigerant network to a zone that is in heating mode. So we're taking all that heat from that server room that's just heating up and it needs cooling, and we're delivering that to the conference room where everyone is waiting for everything to start heating up in there. With Water Source VRF, what's interesting is you could actually further recover heat between systems. Now, with air source, everything is just within a refrigerant network. You can transfer from one location to another in our refrigerant network. Because there's a common water heat sink here, you're actually going to be able to recover it from one source to another. So if you have one floor that's constantly in cooling mode, it's just pulling all that heat out of that space, you could use that, send it up to the floor above that everyone's in heating mode and needs it. So that's an additional efficiency gain that you would get from water source VRF equipment. In addition, geothermal applications are available for the ultimate in energy efficiency. Geothermal, you're not going to see much deviation at all in terms of the groundwater temperature range. So, and if you're able to tap down into that, yes, there is a substantial cost premium for drilling those wells to get to that geothermal source. But if you, especially if that's already existing, you could certainly tap into that for some heightened geothermal efficiencies. Now, these are higher installed costs for water source equipment. They are more complex controls, so I definitely want to bring that to your attention. This is not quite as plug and play with air source equipment. Some other considerations are definitely taken into account. Okay, so now questions you may have. I'm ready. I have my project. I have my design. I'm ready to go. I want to find a contractor and I want to find the right contractor. So we want to make sure that you are armed with the right questions here. So asking, why is the proposed technology a good fit for my building? Feel free to poke holes in it. If you've learned anything in this presentation about, hey, maybe this is not the right fit. I didn't consider before that the tenants may ultimately be owners of this condo down the line. Is that something we may not want to amend? It's an excellent question. Has the proposed equipment been properly sized for my building? This is an excellent, excellent question that everyone should feel empowered to ask to make sure that we've properly accounted for the D rates associated with your climate. Last thing we want is for on a design day situation where everyone needs the full amount of heat in the system, our outdoor unit wasn't sized accordingly and its D rate's only able to deliver 70% of its heating capacity. If you need 80% of the heating capacity, you're going to fall short. So we want to make sure it's been properly sized. How do install and operating costs compare to alternatives? The reality is there's, this equipment, VRF and heat pump equipment is installed with copper piping. Copper piping, there's certainly a premium on it. So you want to ask the question about total cost of installation. And when it comes to total cost of installation, don't let sticker price just shock you. Also consider your operating costs. Consider the efficiency gains you're going to be getting with this system. Remember that analogy before, walking your dog over letting the dog walk you. If you have a single stage compressor, that is not going to be operating efficiently. That's just going to be on, off, on, off. Has anyone been in a car with someone who only just stepped on the gas or slammed on the brakes? It's not comfortable. You want a comfortable ride. All right, has the designer, contractor, or installer completed the manufacturer training on the selected equipment? Please feel free to ask this question to the person who's going to be installing your equipment. We want to make sure that they know how to install our equipment. I'm a Mitsubishi representative. If I find out that a contractor installing the equipment has only gone through Daikin training, that's a concern. There are different considerations and different install practices for different manufacturers. Different manufacturers have different rules you need to follow about pipe bends or traps in the lines of oil considerations. We want to make sure they've gone through the manufacturer-specific training. And lastly, when was the contractor's last install of a similar scope? Definitely a good question to ask. If someone's been working on small scale, maybe single phase VRF systems, and they just won a job that's 3-phase heat recovery with 5 or 6 sub BC controllers that is just all over the building, may want to make sure that they are comfortable with the type of system they're installing. So these are all very good questions to ask about when you're finding a contractor. When you want to find that contractor, feel free to go to the manufacturer's website. We all have a find a contractor resource accordingly. And if you type in your zip code, you're just going to find all the contractors who have been trained up and completed that training and have a certain certain number of staff on hand who has completed that training recently. We also have a schedule of upcoming training. And that applies for more than just installation. And this is more than just the guy who's going to be, connecting the pipes and charging the system. We have installation for anyone who, we have training for anyone who's interested in going through an application-specific course. I want to learn more about what to look for when I'm walking a site. In fact, right now, Lauren, Alex, and myself were in the process of developing an energy auditor specific presentation to better arm the energy auditors out there to when you're walking into a building, what are you looking for and where should your mind go in terms of the potential options? In terms of incentive and grant programs, this is absolutely something to keep top of mind especially when you're looking at the sticker price of your capital cost of equipment. The state of Massachusetts, as well as other states in the New England area, they have incentive and grant programs that are geared towards reducing the capital cost of equipment for a heat pump installation. And this is going to drive down your upfront costs, and it's going to make the total cost install a lot more palatable and a lot easier to swallow, especially when compared to other more conventional systems. So we're definitely going to continue this conversation a little bit further. Lauren, if I'm not mistaken, we're at a point now to turn it over, or if I'm getting ahead of myself here.
Let's actually try to answer some of the questions first, and then we will have the speakers about Mass Save.
Absolutely.
And I want to remind people to put questions in the Q&A. There have been a few that have come in through the chat, but it's easier to keep track of them if they're under Q&A. So Mike and Alex, do you want to pick some to talk through?
Just going to run through this right now.
Okay.
Mike, should we start from the top or?
Please go ahead, Alex, if you want to. I'll just take a sip real quick, actually.
Sounds good. John Walsh is asking about the loss of efficiency in multi-head units due to modulation issues. So I'm not exactly sure in terms of issue. Is it a cycling issue? I mean, something important to remember is that all these systems are inverter-based systems. So if you have a unit in a zone, if it's sized properly, it should modulate up and down depending on what it needs for the space. In terms of modeling that to how inefficient the system is, I'm not totally sure. I'm just wondering, Mike, if you have any insights on that. But
my thoughts on it, if I'm not mistaken, John asked that question right before we got into the single speed versus variable speed compressor discussion. And yeah, certainly you're going to be having efficiency gains by having that individual steps control over your compressor. The loss of efficiency in multi-head units due to modulation issues, I would say that if anything, having more zones on a system, a more diverse load is going to give you a higher ability for your compressor to individually step up and down in order to deliver spot heating and cooling accordingly. So the more diverse your system is with the wider range of different types of zones, you actually could achieve even more efficiency. And I would say that specifically, it goes for heat pumps in terms of the ability for the compressor to step up and down, but especially for heat recovery, for the ability to recover that heat and deliver it to different locations.
Dennis asked a bit about resizing of ductwork and all that stuff. I think I addressed that a little bit in the retrofit section, but it is possible. It depends on exactly the application. If the ductwork was sized for the right design CFM, it is possible to reuse it for an existing project. Derek is asking about, will you touch high level on where gas-fired heat pump technology is as of today? I'm not sure if everybody's familiar, but essentially what Derek is asking here is about, to me, this sounds like gas-fired VRF is what I would call it. Instead of running your compressor using electricity, you're actually going to run your compressor using gas, natural gas. This is a technology that has been around. Where it is today, it could have an application in situations where there's not enough power for a specific building and there's no interest in upgrading the electrical infrastructure for new air source heat pump equipment, and a gas-fired heat pump is preferred over upgrading the electrical infrastructure. So, I mean, high level, it is an option out there. Is it common? Certainly less common than traditional electric air source heat pump technology. For sure. So, but there are options for that for building owners. If the building has a very high demand from the grid, sometimes it will be looked at for sure. Those machines are quite, it's almost like a gas engine inside of one of these units essentially. So you do have a lot of, you do have some maintenance item definitely to keep in mind if a customer does go that way. It's like a traditional car, you need to change the oil inside your machine. So just wonder, Mike, if you have any thoughts on that.
I think you covered that. I myself, Mitsubishi doesn't delve into the gas-fired heat pump technology, so I would certainly defer to you for that question, but that sounds like you covered it. I see a question here from Michael. Would you asking to explain the ROI benefits of heat pumps versus electric resistance, oil, propane, natural gas, and other fuel sources? It's a good question. We talked about COP as kind of a good baseline determination. If we're talking fossil fuel, we're talking about the heating side of things. And yeah, if we're talking, for fossil fuel driven furnaces, boilers, we're looking at 85% to 100%, or rather 98% efficiency or COP. For heat pumps, you're looking at north of 2. So from a dollar amount standpoint, if someone says the question, I paid $300 for my electric bills this month, if that was an electric resistance, for example, if you're only getting a COP of 1, that $300, if that $300 was spent on a heat pump, you're getting twice as much heating output. And ultimately, that's where the ROI comes from. It comes from that ability to more efficiently use electricity for that space in order to provide that heating. I see a similar comment here that overall COP is taking into account the COP of the heat pump as well as the efficiency of the power plant that's ultimately going to be delivering that gas to you. That's an excellent point, and that's referring to the strategic electrification initiative, where that's talking about electrifying both the end users end of the spectrum, heat pumps, as well as upstream to the actual electricity generation standpoint. Certainly want to get more renewable technologies for energy generation, hydro, wind, solar, et cetera, in order to make the whole grid more green. But it certainly is a good point to consider the overall COP takes into effect the end user as well as where your electricity is coming from. Alex, do you have anything to add on that one in particular?
I agree, Mike, with everything said there. In terms of aux heat, in terms of demand charge reductions, is this referring to different types of controls option over Wi-Fi, which does allow for utilities to kind of limit, I guess, the amount of heating or cooling and switch over to a different source depending on if it's referring to that, then there are some options on the controls end for that.
Agreed. Yeah, demand response is definitely each manufacturer has their own. I believe all manufacturers have some accessory to bring that technology, bring that aspect into it. Certainly quite a few slides on the demand response aspect. But with that said, a heat pump technology, we do have accessories to bring that in onto our system in order to actually comply with that demand response.
Agreed.
I see a question here about short cycling, specifically when oversizing the outdoor unit. That's an excellent question. And that's why we want to make sure if you are going to be oversizing your outdoor unit, if you're oversizing it for the specifically to overcome any derates, certainly you want to make sure that you're not running into a situation where you're below the minimum capacity of the unit. There's a lot of steps with the compressors. They're able to ramp up and down. On the down end, they're able to ramp down to about 15%. Below that, they're going to be oversupplying the heating and cooling to the space. So when you oversize your outdoor unit, you want to make sure you have a diverse load connected to it to ensure that you are always going to have more than that minimum connected, minimum demanded load from the space. So it's a great question. It's part of the consideration where we're demanding that. It's why that oftentimes we're not going to oversize a one-to-one VRF system. When we think VRF, we think multi-zone, but they're out there. There are systems. We have an 8-ton outdoor unit connected to an 8-ton indoor unit. So we want to make sure if we're going to be oversizing on the outdoor unit, we're going to have a diverse enough load on the interior space to make sure we have enough load to properly run that system. Anything to add there, Alex?
I agree with that. Fresh air for ductless equipment. That's absolutely of importance these days. Depends exactly on what kind of ductless units you're talking about. If you're talking about a wall-mounted unit, those do not have fresh air connections right on them. But if you are talking about a cassette, as Mike talked about, a 2x2 cassette or 3x3 cassette, those do have options to integrate fresh air right into those units. And in terms of mitigating air quality issues, some of those cassettes also have filtration available for them, higher filtration options, such as MERV 8 or 13 filters on them. So those are options for ductless units. It depends, a little bit depends on which exactly ductless unit you're referring to there, David.
Yeah, so every manufacturer is different when it comes to that. I would recommend looking at the respective manufacturer's literature to determine whether the indoor unit type is compatible with an outside air knockout in order to deliver that directly to the space. With cassettes, they have a limit on the number of CFM, I believe about 50 CFM approximately delivered directly to a cassette unit. Anything larger than that, there's actually potential to get a whistling noise within the cassette because you're just delivering way too much fresh air to it. So for situations like that where you have a zone served with a fan coil that doesn't have an outside air integration, you could still integrate that with the space, whether that is an occupancy sensor, whether that's literally by detecting a person, whether it's by CO2 levels for demand control ventilation, et cetera. So these are all options for tying in these fresh air applications to heat pump technology.
In terms of Penty's asking about, Michael's asking about heat removal of the various types of heat pumps. Mike, you did touch on that a little bit. So these are mostly sensible systems. If you're talking about, using VRF systems for commercial applications, they're usually sensible systems. They will remove latent, but if you have a high latent load, it is important to keep that in mind and to perhaps consider other types of dehumidification additionally with the VRF system.
So Beth asked a question: if you have hydronic for heat and forced air for AC, what is the best retrofit option? Obviously, with that alone, neither Alex nor I would just go right into an answer and say, this is the best response, just because every building's different, every application's different. But with the information you've given here, we have existing hydronic for heat. If it's a functioning system, it's a good legacy system, building owner is interested in keeping that online, that's perfectly fine. We could keep that on there, stage that ideally as our second stage of heat. Then we'll determine what's going to be the trigger for that, whether it's going to be the space temperature is unable to keep up with the set point, or based on outside air, if we want to move to a more cost-efficient method of heating. That would be definitely how we handle for heating. On the forced air side of for AC, I personally would move to a more traditional zoned approach for fan coils in the individual spaces. But that would ultimately just be dependent on the layout of the building. Alex, would you change anything on that?
No, I agree with that. And it also depends a little bit what type of building we're looking at here. Is this an office building? Is this, more of a multifamily application? It does depend a little bit to what, which one's dominant in terms of sizing as well. So I agree though, Mike. We have a question here from Edison with an existing hydronic system. How does an air to water distribute cooling? So if you do have an existing hydronic system, if you wanted to, I think this question is referring to the retrofit application slide. If you did want to add a air source heat pump chiller, which could deliver chilled water, that would kind of distribute cooling to your space. If the existing is hydronic, as you're looking to upgrade the equipment, that's my thought from that question. But
I agree with that one. Yeah, for retrofitting existing hydronic systems, that would require a bit more robust of an analysis as to how the existing system is currently laid out and what the possibilities are. Air to water, it's a bit more nuanced of an application. Just speaking from my own personal experience with an air to water project I'm working on right now, there are a lot of questions to consider here in terms of what's being delivered. So what I'm working on a project where we have an air to water hydronic system that is going to be controlling a condenser water loop. So the VRF system is ensuring that a 90-degree water loop is running throughout the building at all times. And that loop is being served by water source heat pumps in individual spaces. It's not the most efficient way of delivering to the space, but it offers the ability for simultaneous heating and cooling for every individual unit by having that. So that is, and that would work by circulating the 90-degree water. If it's either in heating, we add heat to it in order to get it up to that level, cooling, vice versa, et cetera, just like that. Anything hydronic related, I would certainly caution myself from just speaking in broad terms on, because they have very nuanced answers when it comes to the hydronic side. And that kind of ties into the next question. Can existing hydronic or steam radiator heat distribution systems be fed from a water to water system? I don't want to just give a blanket yes to that, just because there are various considerations that we do want to take into account. But theoretically, I'll say theoretically, yes, but not absolute yes, depending on the layout of that system. We want to make sure that the water to water system we're looking at is going to be delivering water at the temperatures you need for your system. That's going to be a big factor. What are the entering water temperatures you need for your coils, or the space you need to serve, et cetera. I'm just going down the list right now. David also asked, what distance, I imagine physical linear distance, is efficient between VRF systems and spaces or buildings being conditioned? It's an excellent question. If we're talking about VRF systems, there's certainly going to be a D rate associated with the total length between your condense units and the first joint. That's going to be one of your main values to assess whether or not you're exceeding any design conditions. But typically, the D rate associated with it, the efficiency loss associated with that extended run, it would need to be quite long. I'm talking hundreds of feet long before you're ultimately going to start seeing any sort of efficiency drops. And even if you top out on the total length that you're allowed to install, the total efficiency loss from that is going to be ultimately negligible compared to heating D rates with ambient temperature. Alex, would you agree with that?
Yep, agree. At what MERV Quentin's asking, at what MERV can I start to restrict the airflow on my fresh air intake? So there's a lot going on in this question. So in terms of fresh air intake, so let's say you have a ducted, so I'll take an example. So as a ducted indoor unit with a filter on the back, let's say you do have a little plenum box on the back of the fan coil, and you do have a fresh air intake that goes into the plenum and then into the filter and then into the unit. In terms of MERV rating, so MERV rating, if people aren't familiar, is specifically referring to the filtration efficiency of the filter. So it does depend a little bit on your unit. Can it withstand the higher static caused by a higher efficiency filter? If the answer is yes, is the filter clean? If the filter is clean, filter manufacturers have data for the amount of pressure drop. It does that filter actually takes up by the unit. So if a clean filter will use, let's say 0.15 inches of static, when it's loaded, it could use 0.3, 0.4. If it's really, really full, then it could eventually cause the unit to stop having air go through it because it's restricting the airflow to the unit. So I do think it's a little bit, it depends a little bit on what filter you're using. It depends on the unit you're using. If the higher filter from the higher filter drop can be overcome by the unit. And is your filter clean or is it dirty? I guess that'd be a third point. So kind of a long-winded answer, but hopefully that does help, Quentin. Michael's also mentioning wastewater, which is an excellent point. Agreed. I mean, if you can use wastewater to preheat some of that heat coming into your building, some of that water entering in as it's leaving the building, that's an excellent way to recover some of that energy. So I agree with that comment. That's an excellent point.
I want to jump in and make sure that we have time for the presentation. Alex, can you stop sharing your screen so that we can have the Mass Save folks take over? And while they speak, Alex and Mike can keep working on addressing the questions that are in the Q&A. So we will try to get to all of those. And if you have questions you haven't gotten a chance to enter yet, please go ahead and do so. So we have Ryan Willingham here from Eversource, and Grayson Bryant was planning to join us from National Grid. I'm not sure if he's made it yet. So I will pass it over to Ryan. We can see your, it's in speaker mode. Do you want to switch it to where we see the full slide? Okay, there you go, Ryan.
All right, good afternoon, everybody. So my name, like Lauren said, my name is Ryan Willingham. I work for Eversource, and I'll be presenting the heat pump and electrification offers from Mass Save. So for those of you who don't know, Mass Save is a collection of 5 utilities in the state, along with Cape Light Compact, who are charged with delivering energy efficiency services to our customers. As one, we are Mass Save. We have a common goal of helping both residents and businesses save money and energy. Just very quickly, I'll be going over the program offerings. That's to talk about prescriptive heat pumps, what we do for custom projects, also touching a bit on the instant incentives, also known as the midstream or upstream offers, as well as some training and resources that we have available for contractors. So first, I'll start with the program offerings in the prescriptive heat pump. As many of you have heard, we are offering $2,500 a ton for air source heat pumps, $3,500 a ton for VRFs, starting at 5.4 tons, and $4,500 a ton for ground source heat pumps. Now, these prescriptive offers are available for those customers who are displacing fuel oil, propane, natural gas, or electric resistance heat. And these are available for simple systems up to 50 tons. Here are the minimum efficiency requirements. So for less than 5.4 tons, we do have a qualified products list located at that URL, and that aligns with the residential product list as well. So it's all one qualified product list. And then for the larger air source units and as well as the air source VRFs and ground source systems. Those are the minimum efficiency requirements. And I believe Lauren will be sharing these slides, but these are also available on masssave.com. So some key points to note: this is a fuel reduction or fuel displacement incentive. So we are paying for you to displace, again, natural gas, fuel oil, propane, or electric resistance. This is for partial displacing systems as well as full displacing systems. So if you are doing a partial displacement, we do require that you have an integrated control system so that you can automatically switch between the heat pump and the fossil fuel system whenever it's advantageous. We don't require a specific switchover temperature, but we do recommend that it's 30 degrees or below. Again, this is for simplified projects. So we do have a threshold of 50 tons or less. If you have a project that's greater than that, it would have to either go custom, or you could speak with your program sponsor and we could guide you on how to deal with that. And these are for retrofit or changing out of existing systems. So if you have a new construction project, please contact your program sponsor. We do offer incentives in that space as well, but not these incentives that I just laid out. If you want more information, that's the MassSave link. It's just masssave.com/CI-HVAC. Just a short URL. So now I'll jump really quickly into the custom project. So any project that's over 50 tons or it involves a complex distribution system, if you're doing something where you are adding a DOAS and VRF, for example, or you have something that has different a complex distribution system, you may need to go down this custom pathway. And it's very similar to MassSave's standard custom offer in the sense that we want to calculate the savings and cost, and we will tailor an incentive to help you and the customer meet their needs. I will stress that although the $2,500 and $3,500, $4,500 ton incentives are not available through the custom path, we are just as committed. So we are just as committed to supporting those projects. So we don't want to give a single incentive amount, but we are still committed to supporting those projects. Now, I'll briefly talk about the HVAC instant incentives, which again is if you've been familiar with our programs, you may know it as the upstream or midstream program. This is where we offer an incentive right at the distributor at the point of purchase. And these are reserved for water source heat pumps and water source VRFs. We still also offer incentives for RTUs as well as some pumps and some controls. Updated for 2022 in this HVAC in the midstream or instant incentive space is that because we have those incentives on the downstream side, we no longer offer those at the point of sale. So no longer at the distributor level do we offer incentives for air source heat pumps, air source VRFs, and ground source heat pumps. But we still want to engage with our distributor partners so they can help sell the best product for the project at hand. And so I'll briefly get into some of the training and resources that MassSave has available. For many folks, we find that heat pumps are new and they're unfamiliar technology for many customers and contractors. They are, compared to energy efficiency, there are operational cost considerations as well as installation cost considerations. And we realize that energy efficiency competes with other business priorities. So to help with this, we are standing up a contractor network, which we call the HPIN or Heat Pump Installer Network. And this HPIN is not a requirement for contractors to join the HPIN at this time for 2022. We do expect in 2023, we may make it a requirement in order for the contractor and the customer to receive an incentive. We're always looking for new topics to help our customers and help contractors work in this space. So we will be offering trainings through that HPIN network. Some of these training topics include benefits of electrification, how to leverage the incentive offers. Weatherization has become very important, as Mike and Alex have talked about as well. But pairing weatherization with heat pumps can really lead to the best outcome for the customer. Other resources, we're at a MEEP training now. MEEP offers trainings, also manufacturers like Alex and Mike. ASHRAE has some trainings, and the Mass CEC. We will be sharing these slides, but here are some contacts for the different Mass Save sponsors, where if you have any follow-up questions asked after this meeting, I'll be hanging around just to answer some questions that may come up. But beyond that, you can certainly reach out to these folks to get some answers to project-specific questions that you may have. So that I ran through that kind of quick because I think many of you may have been a part of the Mass Save Business Partner event or the Eversource Only event. So some of this may be repeat information for you. So I just wanted to present that pretty quickly and get to any Q&A questions that we may have.
Thanks, Ryan. A couple people have already put questions in the Q&A box for you. So it'd be great if you could go ahead and open that and answer those. And I just wanted to let everybody know I just put a link to in the chat to the slides again for anybody who missed it earlier.
Okay. Okay, so the first question is from Patrick on the residential home heat pump $10,000 incentive, whether or not that overrides the dollar per ton. The answer is yes, it's an either or. The incentives that I just laid out were for commercial and industrial. I sort of made that abundantly clear. But for the residential offer, the whole home offer, $10,000 is it's an either or. You can't get both of them. And I believe that one also requires weatherization. The second question is from Tom. Are Mass Save incentives available for municipal buildings? Yes, they are available for municipal buildings. They are not available for customers served by municipal light plants. So if they have municipal gas or electric light plants, they are not available for those. You have to be served. You have to be a customer of one of the utilities at the bottom of the screen. Are closed loop ground source heat pumps using polygol eligible for incentives? I believe so, John, but reach out to me after the fact. And are we still using EFI to rebate processing? No, we did move on to a different company to do rebate processing for the 2022 calendar year.
Are there any other questions either for Mass Save or for Mike and Alex? We have one more.
Yeah, so for heat pump water heaters, is there a list of contractors that will install this since the rebate is coming from the contractor? Right now, Mass Save does not have a list of contractors for heat pump water heaters. That's going to become an instant incentive. It's in the final stages of being finalized, but we don't have a list of contractors at this time.
I could speak personally to Mitsubishi, our own commercial domestic hot water solution. We are in the process now of training up local contractors on this particular type of product. We have a number of contractors who are trained up on it. because we personally just rolled out our commercial domestic hot water heat pump system. If you have any specific questions on it, please feel free to reach out to Mitsubishi, myself directly about that question. Domestic hot water heat pumps are certainly in their infancy, especially on the commercial scale. So definitely would defer to manufacturers specifically for those types of questions.
Thanks, Mike. So another question about who the rebate processor is, it's going to be Energy Solutions, and I believe they also do the residential side, but that's just for 2022. I think we will be going out for bid for 2023 and beyond.
Okay, well, it looks like we've answered all of the questions that people have asked us today, and the slides have contact information for all of us, so you can follow up if you have any other questions. Thanks so much, Mike and Alex, for giving a great presentation, and to Ryan and Grayson for joining us for Mass Save. And we'll end it here. Have a good afternoon, everybody.
Thank you, everybody.
Thanks.
Thank you.